I'll conclude with a summary of the essential aspects of conservative forces and of the general relationship between conservative forces and their corresponding potential energies. So our definition of a conservative force is one that depends only on where the objects involved in the interaction are. That is, depends only on position. It does not depend on how the objects are moving, so it doesn't depend on velocity. Does not depend on other forces, other interactions that may be occurring, and does not depend on the object's history. That is, the force is not a function, not an explicit function of time. So it is a function, can be written as a function of position only. Next key point, the work done by a conservative force is always path independent. The work done by some general conservative force, C for conservative force here, is always equal to the opposite of the change in the corresponding potential energy. For every conservative force, there exists a corresponding potential energy, and the work that's done by that force will depend only on the initial and final position, in that it depends only on the initial and final values of the corresponding potential energy, which is a function of position only. So the work done does not depend on how you got from point A to point B, does not depend on the path you took or on how long it took to get there. That is path independence. It only matters where you began and where you ended. Last point, which I'll need to elaborate a bit more because we haven't discussed this thoroughly yet. Conservative forces act in such a way that they always try to minimize the potential energy of the system. This language is a bit anthropomorphic, so to be more precise, I mean that when a conservative force does positive work, the corresponding potential energy is always reduced. That comes from this equation right here. When the work done by a force is positive, so when it sort of succeeds in pushing an object in the direction that it is pointing, that's why I say the conservative force is trying to minimize the potential energy. When it does that, potential energy goes down. So if I look at a small amount of work done by a conservative force, an infinitesimal amount of work done, that'll be equal to the opposite of an infinitesimal change in the corresponding potential energy. And this small amount of work could be represented by that conservative force acting over a very short path, just taking one infinitesimal step forwards, one dotted with a little displacement vector here, gives us a tiny change in potential energy. This dot product could be written as the sum of the products of the components of those two vectors. So fcx dx plus fcy dy plus fczz dz if there were a z term, but you get the point. And I want to focus specifically on one-dimensional forces here. Those are the examples that we have considered. So if we have a force only in the x direction, then this equation would reduce to this, or if the force was only in the y direction, it would reduce to that. And we see that we're going to be able to sort of rewrite this relationship as a derivative relationship between potential energy and force. Here, let's look at our examples again. Gravity and elastic force. For the force of gravity, the gravitational potential energy is a function of vertical position, y, this linear function of vertical position, y, mgy. So the higher you are, the more gravitational potential energy the system has. And the corresponding gravitational force is a constant, the constant gravitational force, negative mg in the y direction near the surface of the Earth. And so note from this relationship here that this can be rewritten to show that the y component of gravity is equal to the opposite of the derivative of the gravitational potential energy with respect to y. That is, minus mg is exactly equal to the opposite of the derivative of gravitational potential energy with respect to y. Take minus d dy of this, and you get that constant right there. here we see that according to this gravitational potential energy function, mgy, we can always lower the gravitational potential energy by going to a lower value of y. There's no minimum on this linear function. It keeps going down forever. So we can minimize gravitational potential energy by continuing to always go to lower and lower values of y, as long as we stick near the surface of the Earth. So gravity as a conservative force is always trying to minimize gravitational potential energy by trying to bring the object to a lower and lower value of y. You can never get low enough for gravity. That is, this derivative never goes to zero. You never reach a minimum. The derivative of the potential is a constant. This line has a constant slope. Contrast that to our spring force, our linear elastic force. Here, our spring potential energy is this quadratic function of displacement from the equilibrium position. That's x here, how far away the spring is from its equilibrium length. So x is your strain of the spring, the stretch or the compression. And it's this quadratic function with a minimum. Here, our corresponding spring force, this restoring force, Hooke's law here, this linear restoring force minus kx, this could be related to our spring potential energy. Going back up here, there's no y component there, so we see that the x component of our spring force could be written as the opposite of the derivative of the spring potential energy with respect to x. This equals minus the derivative of the spring potential energy with respect to x. Let's check that. If we take d dx of this, we get kx, and minus d dx of that gives us minus kx. So yes, indeed, the opposite of the derivative of the potential energy gives us the corresponding conservative force. And this derivative does go to zero at one location, here at x equals 0. There is a specific place where we are able to minimize the spring potential energy. So the spring force, the elastic force, as a conservative force, it tries to minimize the spring potential energy by always pushing the object towards this equilibrium position. That's the nature of this restoring force here, always pushing back towards the spring's original length. It elastically tries to restore it to its original length. And so we can generalize beyond gravitational forces and spring forces. There are other conservative forces in nature. There are electric forces and any number of other examples. So what we're seeing here is that for a one-dimensional conservative force, we've got an equation that is kind of the counterpart to this equation. This is the first most important equation relating conservative forces and the work that they do to corresponding potential energies. Here, the counterpart is the second most important relationship between conservative forces and potential energies. We see that for a 1D force, if your force is, say, a function of x, then the x component of that force is equal to the opposite of the derivative of the corresponding potential energy with respect to x. If your force is a function of y, then the y component of that force is the opposite of the derivative of the corresponding potential energy with respect to y. Or if you have a radial force, say, in circular motion, then the radial component of your force, if your force is a function of radial position r, will be equal to the opposite of the derivative of the corresponding potential energy with respect to r.